Hi guys. Welcome to Science Moment. A place to ask the big questions, to seek the hidden truths, and to marvel at the sheer scale of the universe we call home. Let's pause for a moment. Right now. Imagine this, if all sound on Earth suddenly disappeared. No car noises. No people's voices. Not a single signal being sent. It's just you, and the night sky. You look up. The stars silently gaze back at you from distances of tens, hundreds, even millions of light years. And then a question arose, a question that has haunted humanity since we learned to think. Is there anyone else out there? Not a distant planet. Not some strange creature. But another intelligence, asking the exact same questions we are. Because if the universe is truly unimaginably vast, if there are hundreds of billions of galaxies, each galaxy containing hundreds of billions of stars, and countless planets that could harbor life. So why is the universe so eerily silent? No signal. No message. Not even a greeting. This silence has a name. It's called Fermi's paradox. And when we delve into that paradox, we're not just asking questions about extraterrestrial beings. And that began to raise questions about the very fate of humankind. Chapter 1. Introduction: humanity's most obsessing question since humans first gazed at the night sky. A quiet but persistent question has lingered in our minds. Are we alone in this universe? It's not just a scientific question. It's a question of humanity's place, the meaning of existence, and whether our intelligence is a rare accident or simply a normal phenomenon in the vast cosmos. The Milky Way, the galaxy we live in, contains approximately 200 to 400 billion stars. Each of those stars, according to modern observations, is likely to possess at least one planet, and the Milky Way is just one of hundreds of billions of galaxies in the observable universe. In other words, the number of planets in the universe is so vast that the human brain cannot intuitively comprehend it. Even if only a very small fraction of them have conditions suitable for life, the number of worlds that could potentially harbor life is still enormous. What if intelligence could develop over time from simple life? What if intelligence tended to build technology and explore space? The next question is almost inevitable. Where are they? This question was posed simply in 1950, when Nobel Prize-winning physicist Enrico Fermi was chatting with colleagues at lunch. As the conversation revolved around the possibility of extraterrestrial life, Fermi suddenly paused and asked a short question. So where are they? No complicated diagrams. No lengthy equations. Just a very human question, but one that contains a huge contradiction. That contradiction is now known as the Fermi paradox. On the one hand, everything we know about the universe seems to strongly support the possibility of intelligent life existing beyond Earth. On the other hand, we see absolutely no clear evidence of them. No reliable radio signals. No giant space structures. No ancient probes. No messages left in the sky. There was only silence. This silence isn't like not finding anyone in a small room. It's like walking into a huge stadium, supposedly packed with people, yet hearing absolutely no sound. No talking. No footsteps. Not a single sign of presence. And it is precisely that silence that worries scientists. If the universe is indeed teeming with advanced civilizations, then by simple logic, at least one of them must have left a trace. A civilization that emerged just a few million years earlier than us. A blink of an eye on the cosmic timescale would have had enough time to spread throughout the galaxy. But our galaxy still looks desolate. This leads to two equally terrifying possibilities. Or perhaps we are truly very special, almost a rare miracle. Or perhaps something is preventing civilizations from surviving long enough for us to encounter them. And if the second possibility is correct, then the next question becomes chilling. What happened to them, and is that what awaits us? Fermi's paradox doesn't offer an answer. It simply places us before a cosmic mirror, forcing humanity to ask, where do we stand in this story? To begin answering this question, we must return to our most familiar starting point, Earth. Because if we want to understand whether life is rare or not, we need to understand how easily or with how difficult it was for it to appear right here in our own home. In the next chapter, We'll look back at the first moments when life began to emerge on Earth, and why that led many scientists to believe that simple life could be very common. In the Universe Chapter 2, Is Life Rare? A story that begins on Earth. If we want to know whether life in the universe is rare, the only place we can start seriously is Earth. Not only is it humanity's home planet, but it's also the only specimen that modern science has in hand to study life from scratch. Earth formed approximately 4.5 billion years ago in a completely unfriendly environment. Its surface was then an ocean of lava, constantly subjected to violent meteorite impacts. The early atmosphere lacked oxygen, and temperatures were high enough to destroy most complex chemical structures. If there was one place that seemed unsuitable for life, early Earth was a prime example. But what astonished scientists was that as soon as the planet cooled down enough, life appeared. The oldest evidence suggests that simple life forms existed between 3.8 and 3.9 billion years ago. This means that within just a few hundred million years after Earth became relatively stable, chemical reactions had organized themselves into self-replicating systems, a core characteristic of life. On the cosmic timescale, a few hundred million years is not a long time. Compared to the age of Earth, it's almost instantaneous. This leads to a very important question. If life is an extremely rare and unlikely process, why did it appear so quickly? One plausible explanation is that simple life forms are not difficult to create, at least under the right conditions. This view is reinforced when we look at the chemical composition of life. The elements that make up your body, carbon, hydrogen, oxygen, nitrogen, phosphorus, are all common elements in the universe. They are found in interstellar gas clouds, in meteorites, and on many other planets besides Earth. Even complex organic molecules, the foundation of biology, have been discovered in deep space. This shows that prebiotic chemistry is not exclusive to Earth. Many scientists therefore believe that, given the three basic elements, liquid water, an energy source, and a suitable chemical environment, life can simply be a natural outcome, not a miracle. If this argument is correct, its consequences are enormous. It means that bacteria, single-celled organisms, or primitive life forms could exist on countless different planets in the universe. Life, at its most basic level, may not be rare. However, this is also where the story begins to get more complicated. Because on Earth, life has existed for billions of years in incredibly simple forms. It took nearly 3 billion years for life to evolve into complex multicellular organisms. And intelligence at the level capable of building tools, culture, and technology, what we call civilization, only appeared once. This raises a noteworthy question. While life may be common, intelligent life is extremely rare. And if intelligence is such a difficult evolutionary leap, then Fermi's question, where are they, returns, even more alarmingly than before. In the next chapter, we will go straight to the heart of this contradiction, the Fermi paradox, and analyze why, by all logic, the universe should not be as silent as we observe it to be. Chapter 3, The Fermi Paradox, Where Are They? When you put these two facts side by side, a slight feeling of unease begins to emerge. First fact, the universe is extremely old and extremely vast. Second fact, we have not yet seen any clear signs of extraterrestrial civilizations. It is the gap between these two facts that creates what is known as the Fermi paradox. Our Milky Way galaxy is approximately 13 billion years old. Over such a long period, it's entirely plausible that a technologically advanced civilization would have emerged just a few million years, or even a few 100,000 years, earlier than humankind. And in the cosmic context, a few million years is almost negligible. Now let's consider the potential for expansion of such a civilization. Even if their technology isn't far superior to ours, as long as they possess spacecraft that travel at sublight speeds and are self-sustaining, spreading throughout the galaxy is well within their reach. Many scientific models suggest that a civilization could explore and settle the entire Milky Way in just a few million to a few tens of millions of years, a very short time compared to the age of the galaxy. If that had ever happened, the night sky today shouldn't look so empty. We should have seen the unmistakable signs: enormous, unexplained energy sources, man-made structures of star-like scale, or at least communication signals lasting for millennia. But the reality is quite the opposite. We've been listening to the sky with radio telescopes for over half a century. Projects like SETI have scanned millions of stars, searching for signals that might indicate artificial activity. The results so far have been inconclusive. It's not that it's not certain. Rather, it means there's no reliable evidence. This is the core of the paradox. If the probability of the existence of intelligent civilizations is high, then evidence of them should be everywhere. But if evidence is completely absent, then either that probability is much lower than we think, or we are fundamentally misunderstanding something. Fermi's paradox doesn't say that aliens don't exist. It just points out that two of our most common beliefs can't both be true at the same time. The universe is teeming with advanced civilizations, and we don't see any sign of them. One or both of these assumptions must be wrong. Some argue that we may be setting our expectations wrong. We search for radio signals in the same way humans broadcast, but other civilizations may have used entirely different technologies. They may have moved on to more sophisticated, silent, or traceless forms of communication. However, this argument only addresses a small part of the problem, because even if they don't try to communicate, the activities of a highly technological civilization must still leave a physical trace. Energy consumption on a planetary or stellar scale cannot be completely invisible. Another argument suggests that we may have arrived too early. Perhaps intelligent civilizations haven't yet emerged in sufficient numbers for us to encounter them. But this is also difficult to accept, because many Earth-like planets formed billions of years before our own. So why hasn't anyone gone before? It is at this point that Fermi's paradox shifts from an astronomical question to one with profound philosophical undertones. Is there something in the very process of life and intelligence's development that prevents civilizations from lasting long enough? If that's the case, then the silence of the universe is no longer a mystery, but a warning. In the next chapter, we will explore the various hypotheses proposed to explain this silence, from the limitations of human technology to controversial ideas such as the zoo hypothesis. Chapter 4. Theories explaining the silence of the universe. Faced with the Fermi paradox, scientists are not quick to conclude that we are alone. Instead, they pose a more cautious question: what could make the universe seem so silent, even if intelligent life truly exists? From there, numerous hypotheses have emerged, each explaining the silence in a different way, ranging from humble to highly speculative. The simplest hypothesis is, we haven't looked far enough, and haven't looked long enough. The Milky Way has a diameter of approximately 100,000 light-years. Meanwhile, humanity's detailed observational range only covers a very small fraction of this galaxy. Radio signals also don't last forever. They weaken, are interfered with, and easily blend into the cosmic noise. The lack of detected signals may simply reflect the limitations of our technology, rather than the absence of other civilizations. However, this hypothesis has a problem. Despite technological limitations, we are not only looking for signals, but also for traces of energy. A sufficiently large civilization would inevitably consume energy on a stellar scale, something that could be detected indirectly. The silence, therefore, cannot be fully explained by not having observed enough. Another theory suggests that civilizations exist, but are too advanced for us to recognize. Instead of building massive structures or broadcasting powerful signals, they may have shifted to more sophisticated forms of existence: nanoscale networks, distributed artificial intelligence, or ultra-low power consumption systems. In this scenario, civilizations don't disappear, they simply become nearly invisible to humanity's rudimentary observational tools. This hypothesis is intriguing, but also difficult to verify. It relies on the assumption that all civilizations follow a path of maximization and shrinking, while human history shows that technology often expands before shrinking. Nevertheless, it reminds us that the absence of evidence does not mean that nothing exists. One of the most famous and controversial theories is the zoo theory. According to this hypothesis, advanced civilizations have long recognized the existence of humankind, but deliberately refrained from intervening. We were observed like animals in a cosmic sanctuary, allowed to develop naturally until a certain threshold was reached. This lack of contact was not due to helplessness, but rather to an ethical or strategic choice. While it may sound like science fiction, this hypothesis is taken seriously because it explains one thing: deliberate silence. However, it also requires an incredible degree of coordination and consensus among extraterrestrial civilizations, something we're not sure is possible on a galactic scale. Furthermore, we cannot ignore reports of UFOs or UAPs, unidentified flying phenomena. Science approaches these phenomena with the necessary skepticism. Unidentified does not equate to extraterrestrial origin. In most cases, when thoroughly investigated, they can be explained by natural phenomena, human technology, or errors in observation. The important point is, science does not rule out the possibility of extraterrestrial life, but it also does not accept a hypothesis without clear and reproducible evidence. After considering all these hypotheses, a general feeling began to form. None of them were completely satisfying. Each hypothesis only explained a part of the cosmic silence. And it is at this point that scientists began to turn their attention to a more somber, yet more consistent idea. Perhaps the problem wasn't that we hadn't looked closely enough, but that very few civilizations had ever existed long enough to be seen. Chapter 5. Great Filter: the most terrifying theory of all the explanations for the Fermi paradox. The Great Filter is the one that most unsettles scientists. Not because it's complex, but because it's brutally simple. It doesn't attempt to explain the universe's silence with underdeveloped technology or hidden civilizations. Instead, it presents a far colder possibility. Most life forms never overcome one or more extremely difficult hurdles on their way to becoming interstellar civilization. The Great Filter is a concept describing evolutionary steps with an extremely low probability, to the point that most worlds fail at one of them. This sequence of steps can be visualized as follows: from inanimate matter, simple life, complex life, intelligence, technology, a civilization capable of long-term survival. In the universe, if even one link in this chain is nearly insurmountable, then our lack of sight of other civilizations becomes entirely logical. The problem is, we don't know where the large filter is located. If the filter were located very early, for example, at the very beginning of life formation, then the rapid emergence of life on Earth would be incredibly fortunate. This would mean we are living on a rare planet where a nearly impossible event occurred. In this scenario, humanity is the cosmic exception, and the silence around us is simply because there is no one else. It sounds comforting, but it also comes with an unavoidable feeling of loneliness. However, much evidence suggests that simple life may not be so rare. Organic molecules are common in space, and life on Earth formed relatively early. This has led many scientists to suspect that the Great Filter is not an early stage. And if so, then the remaining possibility is far more frightening. The filter might be right in front of us. In this scenario, intellectual and technological development is not the destination, but rather a step into a dangerous zone. A civilization, upon reaching a sufficiently advanced level, will simultaneously possess tools capable of self-destruction. Nuclear energy, biological weapons, uncontrolled artificial intelligence, and environmental destruction on a planetary scale, all are examples very familiar to humankind. The Great Filter was not an external catastrophe, but an internal test, whether an intelligent species was wise enough to survive with its own power. It is noteworthy that, in Earth's history, no technological civilization has ever passed this test for an extended period, because we are only just beginning. Humankind has only been in the industrial and technological age for a few hundred years, and the nuclear age for less than a century. On the cosmic scale, we are still in our very first and most fragile steps. Another perspective on the Great Filter relates to the speed of technological development. Technology typically advances exponentially, while social, ethical, and biological adaptability evolves very slowly. This gap can create a breakpoint, where power spirals out of control. If this were common in the universe, many civilizations could have flourished briefly, only to quickly disappear. And that might be why the universe looks quiet, not because no one ever existed, but because no one existed long enough. What makes the Great Filter hypothesis particularly unsettling is that it turns the search for extraterrestrial life into a mirror reflecting our own future. If we discover simple life everywhere, but find no lasting civilization, it could implicitly suggest that the path ahead is extremely perilous. Conversely, if one day we discover traces of an ancient civilization that existed millions of years ago, that would be redemptive news, proof that the great filter may lie behind us. Until we find that answer, humanity stands in a very peculiar position, between good fortune and potential disaster. We are intelligent enough to question the great filter, but not old enough to know whether we can overcome it. Chapter 6. Is intelligence really an evolutionary advantage? We often assume that intelligence is the pinnacle of evolution. In the human view, the ability to think abstractly, create tools, and build complex societies seems like an inevitable progression of life. But when we look back at the history of evolution on Earth with a cold, hard eye, an unsettling question begins to emerge. Is high intelligence truly the optimal path for long-term survival? On Earth, evolution has experimented with countless different strategies. Vision has appeared independently many times in different groups of organisms. The ability to fly, swim fast, or adapt to harsh environments has also been observed. These traits provide clear and repeated advantages for survival throughout biological history. But intelligence at the level capable of creating civilization is different. In over 3.5 billion years of life history, only one species, humanity, has developed complex languages, accumulated cultures, and technologies capable of transforming the planet. This suggests that intelligence is not a common or mandatory evolutionary path. It may be a very narrow branch, perhaps even a dangerous sub-branch. One important point to note is that high intelligence not only brings advantages, but also comes with enormous costs. The brain consumes a great deal of energy. In humans, the brain accounts for only about 2% of body weight but consumes up to 20% of energy at rest. In a natural environment, this is an extremely costly investment. Moreover, intelligence allows for behaviors that transcend the natural ecological framework. Humans can overhunt, deplete resources, and alter the environment faster than their own ability to adapt. The most successful species on Earth, bacteria, insects, fish, did not need high intelligence to survive for hundreds of millions of years. From this perspective, intelligence can be seen as a high-risk strategy. It offers significant short-term gains, but also opens the door to rapid downfall. The more intelligent a species, the greater its sphere of influence, and when it makes a mistake, the consequences are correspondingly large. This relates directly to the Great Filter hypothesis. If intelligence and technology were not a stable destination for evolution, but a dangerous stage, then many civilizations might have been eliminated shortly after reaching a certain level. Not because they were less intelligent, but because they were too powerful for self-control. Another often overlooked aspect is that high intelligence can undermine natural selection. Technology enables humans to survive without biological adaptation. This reduces traditional evolutionary pressures while creating new challenges at the social and technological levels, where biological evolution cannot keep up. Looking out at the universe, this suggests a grim possibility. Intelligence is not the pinnacle of life, but rather a rare and fragile experiment. Most worlds may stop at the level of simple or moderately complex life, forms stable enough to survive for billions of years without needing to build dangerous technology. In this context, the silence of the universe is no longer incomprehensible. It may reflect a law of evolution. Those species intelligent enough to look up at the sky are also the ones most likely to end their own lives. For humankind, this question is not merely academic. It forces us to rethink how we define progress. If intelligence doesn't automatically equate to sustainability, then humanity's greatest challenge may not be becoming smarter, but rather learning how to coexist with that intelligence over the long term. Chapter 7. The lifespan of civilization, the variable L, in the Drake equation when scientists attempted to turn the question, "Are we alone in the universe?" into a serious mathematical problem. They developed the Drake equation, a formula to estimate the number of civilizations capable of communication within the Milky Way. This equation includes many variables: the number of stars, the number of planets, the likelihood of life forming, the likelihood of the emergence of intelligence. But there is one small, often overlooked variable that carries decisive weight. L, the average lifespan of a technologically advanced civilization. The variable L doesn't ask, will civilization emerge? It asks, how long can civilization survive in a detectable state? And it is here that Fermi's paradox can find its simplest solution. Humankind has only entered the detectable phase about 100 years ago. Since we began broadcasting powerful radio waves into space, Earth has truly become a technological bright spot. Before that, 400s of thousands of years of existence. Humanity was completely invisible to an extraterrestrial observer. 100 years, on a cosmic scale, is almost a blink of an eye. Now imagine another civilization going through a similar phase. They develop technology, start broadcasting, harness energy resources, and then, for some reason, they collapse after only a few hundred or a few thousand years. In that case, the likelihood of the two civilizations coincidentally is extremely low. The universe may be full of civilizations that once existed, but not all existed at the same time. If the average lifespan of a technologically advanced civilization were just a few thousand years shorter, the galaxy would almost always appear empty, even if intelligent life continuously appeared and disappeared. This is a very economical solution. No complex theories needed. No advanced technology required, just a very short lifespan. This also highlights a particular period in the history of all civilizations, the period of greatest vulnerability. It's when technology is powerful enough to cause global catastrophe, but social, ethical, and governance structures haven't yet matured enough to control it. Humankind today seems to be living precisely in that period. If most civilizations fail to cross this danger window, then the variable L will be very small. And when L is small, the result of the Drake equation almost always approaches zero. Not because no one is there, but because no one is there long enough to meet. Another aspect of the variable L is that civilizations can proactively become silent. Instead of broadcasting noise, they can switch to more efficient, discrete forms of technology. Then, the noise phase, the easily detectable phase, is even shorter. This further reduces the probability of observation. From this perspective, the Fermi paradox is no longer a question of extraterrestrial life, but a question of the sustainability of intelligent societies. A civilization doesn't need to become completely extinct to disappear from the skies. They just need to stop transmitting signals. And if that's the general rule, then the silence of the universe is no longer surprising. It simply reflects a cold reality. Intelligence may flicker many times in the galaxy, but very rarely does it burn long enough. Chapter 8. If we are truly alone, try putting yourself in a scenario so uncomfortably silent. It's not just that we haven't found anyone else in the universe, but that there really is no one. No ancient civilizations are lurking. No signals are waiting to be deciphered. No other intelligence has ever overcome the barriers the universe has placed upon it. If that's true, then Earth isn't just a habitable planet. It becomes a cosmic anomaly, the only place where inanimate matter has learned to think, question, and contemplate its own existence. In this context, humankind is no longer just an ordinary creature among countless others. We become the sole dwelling place of consciousness in the entire Milky Way, or even in the observable universe. A small island of thought and meaning, floating in a cold ocean of matter. The first feeling this scenario evokes is not pride, but the weight of responsibility. If there were only one place where the universe knew its existence, its destruction would not be merely a local catastrophe. It would be an absolute silence of consciousness, lasting until the universe cooled and disintegrated. There would be no one left to observe, remember, or tell the story of the stars. From this perspective, the conflicts that humanity usually considers supreme, territorial disputes, ideological conflicts, power struggles, suddenly become sadly insignificant. They are the internal conflicts of a nascent civilization, playing with forces powerful enough to end its own story. If humanity is truly alone, then our ethical question also changes. Protecting life is not just about protecting humans or Earth's ecosystems. It becomes about protecting the possibility of meaning existing in the universe. Each species, each ecosystem, each culture becomes a microcosm of an extremely rare phenomenon, conscious life. This also changes how we view the future. Expanding into space is no longer simply about exploration or conquest. It becomes a long-term survival strategy for consciousness itself. Bringing life beyond Earth may be the only way to ensure that a local catastrophe doesn't wipe everything out. However, solitude also carries an emotional paradox. If there is no one else out there, then any hope of an answer from the universe will never come. No one confirms that we are not alone. No one warns us in advance of mistakes. We are forced to learn, make mistakes, and correct ourselves in an indifferent universe. But it was in that silence that another meaning began to take shape. If intelligence only appeared once, then every moment of human thought, creation, and empathy would be infinitely more precious. Art, science, ethics, and even the clumsy attempts to understand one another, all would become rare manifestations of the universe striving to understand itself. In this scenario, the question, "Are we alone?" is no longer a question about aliens. It becomes a question about what we will do with this unique position. Will we see it as an excuse for despair, or as a motivation for growth? Perhaps the universe does not inherently possess meaning. But if there is a single place where meaning can be created, then that responsibility, however weighty, is a rare opportunity. An opportunity to demonstrate that intelligence does not necessarily lead to self-destruction, and that existence can be preserved beyond a cosmic moment. Whether the alone scenario is true or not, reflecting on it forces us to look at Earth through different eyes. No longer just an ordinary planet in a vast universe, but a fragile yet unique point where the story of consciousness is being written day by day. Chapter 9. Conclusion questions left for the viewer after traversing a path from the formation of life, the Fermi paradox, the great filter, to the possibility of human loneliness. We return to the starting point, not with an answer, but with a new perspective. The universe remains silent. The stars are still there, and the question, "Are we alone?" remains unanswered. If the universe is teeming with life, then humanity is living in an extremely special moment, a moment when we may be one of the very few surviving civilizations capable of questioning and searching. If the universe is nearly empty, then our place is even more special. We are one of the rare places where the universe is self-aware. Human history shows us to have an incredible capacity for creativity, cooperation, and adaptation. But it also reveals an undeniable dark side, a tendency toward division, destruction, and the misuse of power without considering the consequences. In the cosmic context, these inherent contradictions are not merely social issues, they may determine whether intelligence will continue to exist. The Fermi paradox, in this sense, is not a purely astronomical question. It is a philosophical mirror. When we ask, "Where are they?" we are simultaneously asking, where will we be in a few thousand years? Will we become a faint trace in the history of the universe? Or a rare exception that transcends the limitations that other civilizations may have stumbled upon? We may never receive a signal from the stars. Even increasingly powerful telescopes may only show us profound silence. But that silence isn't necessarily nothingness. It could be a reminder, no one else is responsible for us. If true intelligence is rare, then every collective decision humanity makes, about war, the environment, technology, and how we treat each other, carries cosmic weight. They not only shape the future of a species, but may shape the future of consciousness in the universe. Ultimately, the most important question left by the Fermi paradox is not "Is anyone out there?" but rather, if no one else is, are we mature enough to deserve this position? The answer doesn't lie in the stars. It lies in how we live, cooperate, and choose today. And perhaps that is the most profound message the universe's silence sends us. After all the theories, equations, and telescopes pointed into the deep darkness of the universe, we still don't have the answer. Perhaps life is abundant out there. Perhaps civilizations once existed, but vanished before they could meet. Or it could also be a possibility that sends chills down one's spine. We are the only voice of consciousness in this entire galaxy. If that's true, then humanity isn't just a random species on a tiny planet. We may be the only place where the universe is aware of itself. The only place where matter thinks. The only place where meaning exists. And if one day we destroy ourselves, through war, greed, or irresponsibility, then perhaps, it's not just the Earth that's silent, and the entire universe would become quieter than ever before. Therefore, the most important question is not, where are they? Instead, it is, what will we become? Because perhaps, how we live today will determine whether this universe will continue to have people asking questions, or remain forever silent.